uncorrelated, then it is very difficult for you to say something about distribution and find distribution. You have to take into account various factors and math become complicated. So what we do is, next is to basically define another variable. What we are going to do is we decorrelate it, x1, x2, x3 and x4. So we can define a linear transformation like this. Lij is basically x on a certain random variable, and then the resultant is basically uncorrelated. So I think it's called in technical words it's called Cholesky decomposition, I think. Yeah. So the technical term is this. So this way we can find this Lij. So we can Cholesky decomposition, and then we can find the uncorrelated variables. So yeah, when we find the uncorrelated variable and we substitute back into our F statistic, and we kind of get this form of zi's are basically our new uncorrelated variables. So we have this z1, z2, z3 and z4. So this is very familiar. So one more thing, that we know that xi's are normally distributed. So they have a linear, this is a linear transformation. So zi must be normal, they must be normally distributed as well. So when we have the squared sum of normal variables, random variables, then we have chi-square distribution. So this type of thing is basically if z1s are normally distributed and we have a squared sum, then f is basically follows a chi-squared distribution. So yeah, so in that case we have four variables, so independent variables. So there are 4 degrees of freedom here. Yeah, so for chi-square distribution, the mean value is basically simply the the degrees of freedom. So when we have when in the case when the signal is absent, we basically don't have the mean of the data. The data only consists of noise, and we initially considered that the noise is basically zero mean. So yeah, so through that the mean should be 0 for when the signal is absent. So the mean value of the F statistic following the chi-square distribution should only be the degrees of freedom, which in that case is the number of independent random variables. But when we have a signal, then we don't have a mean equal to 0. So in that case we have a term, extra term, which is basically expected value. What we call it the non-centrality parameter. So yeah. So basically the technical word for this is that a non-central chi-square distribution, and when the signal is absent, we follow the central chi-square distribution, centralized chi-square distribution. Yeah, so we have our model, we have our data analysis technique. Then how should we estimate the parameters? Like we basically, but let me go through quickly that we first define the signal model, and then we basically consider data analysis technique, like we are going to use hypothesis testing for our data analysis. Then we went for the log likelihood function, and then we maximize our log likelihood function over AIs, and which the maximized version of log likelihood function is called as F statistic. So we have our F statistic. then what we're going to do is basically first, I told you that there are 8 parameters. There are 4 phase parameters and the 4 basically other parameters which I defined earlier, which basically AIs are depending upon. So what we're going to do is basically through parameter estimation techniques like through template banks and match filtering is I think the term is template. Through uses of template banks, we can estimate parameters. So what we're going to do is basically first we are going to estimate our phase parameters through parameter estimation techniques.
Hold on. Your detection statistic that you have computed, right? If you go back to some of your very first slides, you say, well, if I want to see even earlier on, very, very beginning, perhaps not that early. Let's see, next slide, sorry. Next slide, yeah, perhaps, no, go a bit further, yeah, where you define. So this is a signal model, and in this signal model you have assumed, some phase parameters and amplitude parameters,
yes,
correct?
Yes.
Okay. Then go to where you define the log amplitude, the likelihood the first time. There you go.
Yeah.
Okay. So you see equation 15 and 16. 15 has that HS, which is the signal hypothesis, right?
Mm-hmm.
And then in equation 16, you're actually specifying that you are basically testing what you're testing the non-signal hypothesis H0 versus a specific signal hypothesis. It's not just any signal; it's a signal with those parameters, with those 8 parameters.
Yes.
Okay. So your detection statistic tells you whether a signal with those specific phase parameters is present in the data. What's happened to the amplitude parameters? Well, you don't know which amplitude parameters here are being estimated, but it's the detection statistic has been maximized. So out of all the possible detection statistic values that it could have given you for each combination of the amplitude parameter, it's spitting out the highest one. So the template bank has instead to do with the fact that you now want to test the different phase parameters.
Yes.
And for every phase parameter you have a different waveform, and you can compute a different value of the detection statistic.
Yes.
It doesn't immediately have to do with parameter estimation. It's still just the template bank, just detection. So, sorry, I prefaced all this to ask, in what way did you mean that the template bank is connected to parameter estimation techniques? What do you mean?
Yeah, so basically it's not a single step estimation.
Mm-hmm.
So basically what we do is basically first we maximize our F statistics over these phase parameters through parameter estimation technique, and then using those parameters which we have estimated, then we basically calculate these amplitudes AI. So this is not
okay. All right. So through parameter estimation techniques, you can estimate the amplitude parameters.
So basically, we are not measuring it in a single step.
Okay.
Yeah. So we basically.
So you were talking about the amplitude parameters.
Yes.
Okay.
Yeah.
But so the template bank has nothing to do with that.
Yeah, I just mentioned it for I learned that there is a technique for parameter estimation. We basically use template banks and basically check for each template that how does it matches if it matches our signal or not. I'm not sure how does it work, but I might have said the wrong
Okay.
term here, but yeah.
Okay. Okay, sorry, interrupted you.
Yeah.
Go back to the.
Yeah, so then we estimate the amplitudes for the estimated phase parameter using the analytic formula given, through this equation. Equation 22. Yeah. So this is the maximized version. Right? So through this we can find amplitudes. And then basically we are left with 4 other independent variable parameters which we have to estimate. But the author doesn't discuss it in this paper. So basically, I think in its 3rd or 4th paper, he basically discusses a technique to basically measure those remaining parameters on which basically AIs are depending upon. Let me show you. So AI basically depends on the intrinsic parameter, intrinsic amplitude, the iota, the polarization factor, and the intrinsic phase of the. So these are basically how we measure it, how we estimate it. This is the author is going to discussing that I didn't do it at that time. So basically, as I defined, as I said, that it follows a chi-square distribution. The our statistic in our new random variables follows a chi-square distribution. So these are basically the explicit form of when we have our when the signal is absent. We have this type of distribution for f statistic, and when the signal is present, we have this kind of f statistic. And basically, I3 is basically basal functions. So what we